this is how to solve force problems, beginning to end. Okay, and it all starts out with a force diagram, and we have to analyze our forces, checking to see, which forces are present and in which direction are they going. So I'm assuming that you guys are black belts at force diagramming. That's step one. So let's start with a situation where there's a box on a floor and it's being pulled by a force at an angle. Okay? And so we're going to draw our force diagram. So our force diagram number one has Fg down, Fn up, tension at an angle, and then it would have, I'm going to say that it's not moving. If it was moving with constant velocity, the only difference would be what we call the friction force. If it's not moving, we're going to call it static friction. If it were, we'd call it kinetic friction. Okay, so here's our steps. Step one, let's write those over here. Force diagram. 2, x and y axis. Step 2 is to draw your x and y axis right on top of your force diagram. Notice how I did not draw my force diagram up here on top of my picture. Don't do that. If you need to do that to just see what forces are involved, okay, but then redraw it off to the side and make it nice and big. Because otherwise the lines and everything from the picture, they just get in the way and you can't see what's going on. So you want it to be off to the side. So now, x and y axis. Well, okay, y axis is straight up and down. X axis is this way. Done. Box on ramp, we make the ramp the x axis. I'll show you that one next. Okay, 3. Components, if not on axis. In other words, look at all your forces, and any of them that are not on an axis, we need to turn into x and y components. So look at these. These 3 are all right on an axis. It's Ft that is not on an axis. So Ft needs to be turned into its x and y components. So we can go this way. Ftx. Label it what it is. It's the x component of Ft. It's not just x. That's important because every force we put on this diagram needs to have a name, and the more accurate you can make it, the simpler it becomes, seriously, as you go. Okay, then tip to tail, we go up here to Fty. Why? Because it's in the y direction. The last thing we do, and the key to the city, is we go ahead and we put our net force equations. What is that? Well, a net force equation is all of the forces acting in the x direction, and then we write another equation for all the forces acting in the y direction. We're going to always analyze the forces in 2 directions. That's why we needed these components. See, Ft, it was acting in both directions. Partially along the x-axis, that's the Ftx, and partly in the y direction, that's the Fty. Okay? So what do I mean by net force equation? Well, if you do it exactly like I'm going to show you, it will be this is the easiest way. I'm just telling you, I've taught this for a long time. This is the way to do it. So we're going to start with our x's. So we're going to write an equation that's the sum, remember that sum of the forces in the x direction, and put a colon, not an equal sign there. The sum of your x forces. So start looking in the positive x direction. Only x direction. Don't look at the diagonal. What do we have in the positive x direction? We have ftx. Then we look in the, and so we're adding up all the x forces. That's what the sum of means. So now we're going to add all the negatives in the x direction. That's fs. So I could say plus negative fs if I want, or I can just go minus fs. I usually just go minus fs. Equals what? What do we know about this box? It's not moving, right? So what can we say about the forces acting in the x direction? Do they have to be balanced or not balanced? Okay, they have to be balanced, or it would be accelerating in the x direction. Is it accelerating? No. So they're balanced. That means that there's no net force. Or in other words, when I add these up, it equals 0 net force. So do the sum of the y forces. Colon, not an equal sign. See, because this here, this whole thing is my net force equation. See how it's an equation? It's got an equal sign in it. If you put an equal sign here and then another one there, it's very confusing. Use a colon after that, f of y, the sum of your y forces. Start with the positives. Looking up, Fn. But wait, watch that. There's Fty also going up. So you add it, right? Plus Fty. Now we look down, we see Fg. Minus Fg. Is it accelerating up or down? No. That means that these add up to 0. There is no net force, equals 0. Okay? Now the rest is math. Physics is over. That's as difficult as it gets. These 4 steps, net force, do force diagram, draw in your axis. Any force not on an axis needs to be divided into x and y components. Then write your equation. Take all of your x's in the positive direction, add them up, and then subtract, add them to your negative ones, or subtract your negatives. Do the same thing with the y's. Make sure you scan all the way across. Don't miss Fty. It's easy to miss it. Okay, now the last thing we should do is put tick marks on our force diagram. That's the last thing. In fact, I'm going to put that here just as another item so we don't forget. You want to do this last because look at, if you move this around, you can see that Ftx equals Fs, can't you? Therefore, Ftx equals Fs. But does Fg equals Fn? Is that true? No. Fg equals Fn plus Fty. We can't tick that. We're done with tick marks. Okay, let's do one more box on ramp this time. Same steps. So this time we've got a ramp with a box, and let's say there's a string holding it up. No friction. Okay, so draw your force diagram. Fg is always down. And just to make it more interesting, I'm going to say this is a 30-degree angle here the ramp makes, because I think it's important to work the angle into our final thing. Okay, so which way is normal? Perpendicular to the surface. Which way is tension? Up the ramp. Okay, step 2, x and y axis. Now, the ramp is always the x-axis. That means normal force will always be on the y-axis. Always. Okay, now, what's the third one? components if not on axis. See what happened here? All of a sudden, 2 out of 3 are on an axis now. And FG is the one that needs to be divided into components. You have to be super careful when you do this. Remember the main rule. X and Y axis are perpendicular to each other. They gotta be. Okay, so I see this part is where people make mistakes, is when they make their components. Especially with this one on box on ramp. Now you have your choice. You can go this way and down, or you can go this way and down. I don't think it matters. I usually like to go along the x-axis, but it does not matter. So let's go along the x-axis. F, G, X. Then we have to be careful. This has to be perpendicular, 90 degrees. So that would be like that, right? I'm going to move this over here. F, G, Y. See, this should be along the y-axis. This is along the x-axis. Here's my 90 degrees. That makes FG the hypotenuse. Whatever you're dividing into components will always be your hypotenuse. That's critical to solving these things. Okay, so let's write our net force equation. Let's do the sum of our forces. Oops, that's not really it. In the X, sum of our forces in the Y. Use colons there again. So look in the X direction. Positive X direction is this way. Remember, you got to kind of turn your head to get the idea. But FGX is going along in that direction. FGX minus FT equals, is it accelerating? No, it's not moving. Equals 0. If it were accelerating, what would you do? We'll have an equation for that next unit. So for now, all you would do is put a line through the equal sign so it does not equal 0. That means that there's some number there, that it is accelerating. But for now, we'll just say equals 0 or not equal to 0. So if it's accelerating, you just do a not equals to 0 symbol. Okay, now we do our y's. Positive y is Fn. Negative y, FGY. Equals 0. Now tick marks. Oh, look at this. FGX equals FT. FGX equals FT. FGY equals FN. Double tick it. Those are equal. And the rest is math. Now, where does the 30 degrees fit in? I have a triangle here, and I got 30-degree angle. How do I know how to get it in here? Remember, the ramp was the x-axis. So here's what I like to do. Way down here, somewhere off of this triangle, so I don't confuse it, draw your ramp in. So here's my ramp, here's the floor. Here's my 30 degrees, right? And now watch, since FG comes straight down, I've drawn, this is 90, 30, that makes this 60. Did everybody see I did that? Because this isn't part of my triangle that I just figured out to work SOHCAHTOA to find my components. It's simply showing me a way to get that 30 degrees in the right corner of my triangle so I don't get it in the wrong corner. You know, it's going to be one of the corners. Which corner, though? Right? That would make this side 30 if I wanted to do something with that triangle. If I drew my components the other way, for instance, I could still get that one. This you're going to have to practice a little bit, getting that angle in the right spot. The way I just showed you, pretending this is just extending the ramp, because the ramp is the axis, that I think helps, because we know that FG is going to be straight down. So if this is 30, there's going to be a 90 here. That means this has to be 60, right? It's going to be a complementary angle because of that. All right, good. So now it's just a matter of filling in what they told you in the problem. Write it right on there. Do your SOHCAHTOA. Solve it. That's it.